This is part 3 of my book summary for Amir Aczel, Chance. Chapter 14 is basically about expected gains, and he lays this out really clearly. He says, suppose an investment opportunity has 30% chance of plus $1,000, 20% chance of plus $2,000, and a 50% chance of minus $400. What do you expect to make on the investment? Well, he says that we should be able to do this sort of calculation. And the way to do it is a sort of, almost like a sort of slap 'em through approach. So you've got your 30% chance of $1,000, so you do 0.3 times 1,000, and that equals something, so you make a note of it. Then you do 20% chance of plus $2,000, that's going to be 0.2 times 2,000, make a note of the answer to that. And then you do 50% of minus $400, and that's going to be 0.5 times minus 400. Make a note of that one as well. Now you just sum up all of your results together, you add them together, and in this example you get $500 plus $500. Now most investments will not be that good, but nevertheless this is an example. So if you do this one long term, you can expect to make plus $500. But if you did it short term, it would risk a loss. He then moves on to fair games and zero-sum games. Remember that casino games are not this because of downward drift. He introduces a formula here for roulette analysis. So if you bet on a single number in American roulette, then you have 1 in 38 chance of winning, and you're betting $1 each time. Well, there's a formula for this. So in the first bracket he does minus 1 multiplied by 37 over 38. And that one is, that shows you losing your dollar every time it doesn't land on your lucky number. So 37 out of 38, it's very likely not to land on your lucky number, and you lose minus 1, so you're going to lose $1 every time it does that. So that's the first bracket, and the second bracket is added, so it's first bracket plus the second bracket, and the second bracket is 36 times 1 over 38. So the second bracket represents a situation where it's not likely to happen, but you actually win with your lucky number. So it's a good payout, 36, but it's very unlikely to happen, 1 out of 38. So what's the result of this? So when the two brackets are added together, it equals minus 0.026, approximately. So he says you lose approximately 2.7 cents per spin. And then he says, eventually you will lose it all, which I think is a fantastic message to tell people you might get caught in the trap of gambling. I thought about this later, and in terms of explaining the argument, one of the troubles with this is it's difficult to say when a person stops gambling, because let's say there's someone who does gamble, and they stop gambling on Tuesday. But then they start again next week, on Wednesday. Now, from a mathematical point of view, the time gap doesn't really make very much difference to our probability calculations. So you could say this is the same string, and the person hasn't actually stopped gambling, if you see what I mean. The time gaps don't really make a difference to the mathematical calculations of probability. But essentially, to understand this argument that eventually you will lose it all, the expected gains here are negative. it's minus 0.026. So whenever we say, oh, I've stopped, even though we know that the person's going to carry on later, unfortunately. So every time they've stopped, they should have, the expected gains are less, so it's a negative, so they should have less money to gamble with next time. And if that happens again and again and again, eventually you will lose it all, which I think is the argument which he's making. So both methods here use win and lose payouts. Be careful with the results of this, which should work long term. But that's how you do expected gains. He introduced that topic really well, and I tend to remember it as a sort of slap 'em through method. And then right at the end, obviously, you've got to remember that it should work long term. Moving on to Chapter 15, game strategies. He talks about game strategies for chess, for war, and for stock market competition. One of the things I thought was really interesting about this chapter, Aczel suggests surprise is vital to war. He says an attack is best if the enemy is unprepared. If they can prepare for an attack, then they can defend against it very well, for example. So he says that if a general wishes to attack during the next 12 hours, what he should really do is make it random, to roll 2 dice, and then flip a coin to decide the hour of the attack. Unfortunately, I haven't been able to apply this to my chess games, but perhaps in war games this is a vital tactic. Moving on to Chapter 16, this is where he introduces Bayes' theorem. He has some brilliant things to say about this. He says that Bayes is complicated, it's powerful, and it's often misunderstood. It was 1761, Reverend Bayes was trying to mathematically prove God and other things. So his first example, moving on, is a medical example. And it is a very good example of Bayes' theorem. I think these medical examples where there are lots of false positives is actually the most popular introduction to Bayes' theorem. I'm actually going to use, it's almost the same example, but it's actually from Robert Matthews's book, Chancing It. So here's the example in Chancing It, which is pretty much the same as Aczel's example. It's just I think I can do it a bit better using the Robert Matthews example. So let's go ahead and think through this. So there's in medical science there's a mammogram test for breast cancer, and it's accurate 80% of the time. So 1 in 5 will get this false result. So that's the first statistical piece of information. And the second piece of information is out of 100 people, 5 have breast cancer and 95 do not have breast cancer. I don't know if these statistics are completely accurate. But what goes on here with Bayes' theorem is that they put these two things together and work out some practical probabilities. So you see, it seems good initially that you've got this test which is 80% accurate. But when you put it together with some other information that you're given, the two things can combine together to provide something which is really quite surprising. So first of all, I'm going to go through this with a probability tree, because it works perfectly well with the probability tree, and you get the same answer. And then I'm going to do the same thing, but using Bayes' formula. Should be 5 out of 100 who have breast cancer, and 95 out of 100 going the other way, who do not have breast cancer. Now the second stage of the probability tree should show 1 out of 5 who get the false results, and 4 out of 5 which get a true result. So for those who have breast cancer, that means that 4 out of 5 are going to be true positives, and 1 out of 5 of those are going to be false negatives. But obviously these probabilities are going to combine together, as they always do on probability trees. We multiply and find the end results. So anyway, if you went the other way, if you went 95 out of 100, if you went on the people who don't have breast cancer route, then after that, the second step is also 1 in 5 getting a false result and 4 out of 5 getting a true result. So at the end, basically we have some probabilities which we've calculated, and we get 1 out of 100 are going to be false negatives. So they've actually got breast cancer, but the test has misfired. So they're labelled as negatives, but it's false. 4 out of 100 are true positives, so they have breast cancer and the test has correctly identified them as having breast cancer. And then at the bottom of the probability tree results, we've got 19 out of 100 are going to be false positives. So actually these people don't have breast cancer, but the test has misfired 1/5 of the time. So it's said that 19 out of 100 do have it. Those are false positives. And finally, 76 out of 100 are going to be true negatives. So they don't have breast cancer, and the test has correctly identified them as not having breast cancer. So we got these things, and what we would then do is say, well, if it's a positive result, so what's the probability that the person actually has breast cancer, given that it's a positive result? Now, to do that, it's a counting exercise, a bit like Chapter 2. So you count up, in this case, you consider all of the positive results. So what we're interested in is the true positives over all of the positive results. Now in this case it's a bit of a surprising result, but we take the 4 over 100 and then we divide that by 4 over 100 plus 19 over 100. So it's basically, what we're doing is true positives divided by true positives plus false positives. Now you might notice false positives are very high compared to true positives. So this basically works out as 4 over 23, which is 17%, a very low number. Given that we initially thought this test was accurate, it's basically bad news that only 17%, that if you've got a positive result, you're only 17% likely to have breast cancer, because of there being so many false positives. Right, moving on from there, it's a well-known problem in medical science, and bear in mind that medical scientists are still going to run their tests alongside all sorts of other tests to try and care for their patients in the very best way and to understand the medical conditions. So this problem of false positives in medicine is well known, and it's also a fantastic example of Bayes' theorem. So now I'm going to do exactly the same thing, but actually using the Bayes formula. So if you use the Bayes formula for this, then Bayes formula is probability. Okay, so what's the probability of A given B? And the answer is, using Bayes' theorem, you've got to work out the probability of B given A, which is often quite confusing. Multiply that by the probability of A, and then divide by the probability of B. It's a real classic for Bayes' theorem. If you find these questions where it's, find the probability of this given that, then chances are this is a sort of Bayes theorem question. Watch out for some really unexpected results, or difficult results. You've got to be very careful at every step of the way with this. Anyway, I'm going to show you now how it actually reaches the same result, but in a different way. So what we're working out is probability of it being a true positive, given that it's a positive result. So just expressing it again, we now need to calculate the probability of it being positive, given that it's a true positive. Multiply that by the probability of it being a true positive, and then divide by the probability of it being positive. So some of these steps are easier than others, and I really recommend the probability tree diagram for this to make sure it's right. But it's also really interesting to look at the Bayes formula and how it works. So if you can get your head around this, it's asked us to think about what is the probability of it being positive, given that it's a true positive. And the answer is actually just 1, because if it's a true positive, we already know with certainty that it's a positive. Very odd when you first come across this. Okay, so that's the oddest step that we had to do here. But actually for that, the probability that it's a positive, given that it's a true positive, is just 1. Okay, next up we have to find the probability of it being a true positive. We can take that from the probability tree. That's 4 over 100. And now to find out the denominator, we've got to work out the probability of it being positive. Well, to work out the probability of it being positive, we need to add up all of the positives, which include the false positives and the true positives. So that's 4 out of 100 plus 19 over 100. So this actually works out as 4 over 23, exactly as it did in the probability tree, which is 17%. But if you want to remember the strangeness of Bayes' theorem, bear in mind that our way of doing it just now included this odd step where we had to think about the probability of it being positive, given that it was a true positive, and that actually just meant that there was a single 1 in that space. We got 1 times 4 over 100. This is all too common with Bayes' theorem. Sometimes you'll have things in brackets which actually are 1, or might be 0 in other situations. Okay, so going back to what Aczel said about Bayes' theorem. He says that in just this way, a Bayesian approach starts with a conditional probability, which may be too good to be true. And that's sort of the bare statistics about the test. But the Bayesian method will then reveal the sort of posterior probability, in this case by mixing in the prior probability with the results. He then says something really interesting. He says that prior probabilities are actually quite strange and subjective. Aczel says that if using the test in a hospital full of sufferers, then the prior probability must be adjusted. Okay, he's got one more example in here, which is a good Bayesian example, and he also mentions the Monty Hall problem, which is a fantastic example. You might look up that on Wikipedia, and the 3 prisoners. But anyway, his example is that there are 3 couples up in a skyscraper. Three people sharing three groups of people sharing an apartment, and one of the rooms is GG, one is GB, and one is BB. So that just means girl, boy, just shorthand for that. So initially he's got 1/3 of, say he's looking for the girl-boy room. Initially he's got 1/3 chance of knocking on the right door because he's got no idea which one it is. But then after knocking on the door, a girl answers the door. So the question is, what's the new probability that he's found the girl-boy room? It's a really classic sort of Bayesian question, this, and you know it is because it's got the given that part of it. Well, if you draw this out as a tree diagram, it's not actually that difficult, but you do have to be really careful along the way. So the first stage of the tree diagram is 1/3 for each of the rooms, which are GG, GB, and BB. So, but then the second stage is who answers the door first. So there's a half chance that it's G1 who answers, and a half chance that it's G2 who answers in the first room. In the second room, it's a half chance that G answers, and a half chance that B answers. And in the third room, which is BB, there's a half chance that B answers, and there's a half chance that B answers. Now, there's a quick way of solving this, really. If you start circling the G's right at the end, then you see that there are 3 G's that you've circled. You've circled G1 and G2, because that was from the girl room. And you've also circled the G because the girl could answer in the GB room. So the actual result for this, once you need to do all the calculations properly, but some of it just sort of cancels out. The answer is actually still a third, no improvement, but it's quite surprising and it catches a lot of people out. But essentially, just because a girl answers the door, it doesn't mean that you can leap to any conclusions. You've got to work out the probabilities really carefully, and it still is actually 1/3. Aczel does a Bayesian calculation for this, and it looked to me like there was a 0 times 1/3 in one of the brackets. So, just as we expect, the Bayesian approach makes us consider some things which are slightly mind-bending and odd to see in the middle of the formula. Moving on now to Chapter 17, the normal curve. This was a brilliant introduction to something which everyone comes across in statistics, whether it's in medical science at degree level or at A level in mathematics. And I think this was a really wonderful introduction because he doesn't leap straight into the mathematical calculations of variance and then standard deviation. And instead he gives a very sort of human introduction to some of the interesting developments, which can make the topic really so much more memorable and interesting. So what does he say? He says it's strongly linked to the great German mathematician Gauss, but it was actually discovered earlier by de Moivre. And he says it's sort of like a normal law of errors, which leads to the bell curve. He says the classic thing we all like to remember is that 95% of the results are within 2 standard deviations of the mean. And the mean is right in the middle. The bell curve is symmetrical. So the topmost part of the mound, the highest part of the mound, is exactly where the mean is. He says that bell curves are sort of like a divine law of nature, even with mystical properties. One of his favourite examples is human heights, also percentage changes in stock markets, and there are lots of examples, really, that somehow all turn out to be very much like the normal curve. Next, he explains the tails of normal distribution. And this was brilliant. He says that if you're talking about the tails of a normal distribution, it's actually named after Gosset's picture of 2 kangaroos. So Gosset drew this picture of 2 kangaroos sort of facing each other and almost kissing. And if you take the line above their bodies, it was exactly like a normal curve. And of course their tails represent the tails that he's talking about now in terms of the tails of the normal distribution. So he then slightly laboriously explains all of this about the tails. So the probability of falling to the right of 1 standard deviation from the mean So one standard deviation of the mean, within one standard deviation of the mean are 68% of the results. So this means that 68% of the results are in the middle, one standard deviation from the mean, and each of the tails is going to have 16% of the results, because 16 times 2 is 32, and 32 add 68 is 100, so it's all accounted for. So if the question is, what's the probability of falling to the right of one standard deviation, the mean, what it really means is the right kangaroo tail. What's the probability of that? And it's 16%. In a similar way, if we're using two standard deviations of the mean, then that means that 95% of the results are in the middle, and 5% is spread between the two tails. So the rightmost tail has 2.5% of the results. He then says that if you're using three standard deviations of the mean, that means that 99.7% of the results are in the middle, and that means that there's 0.15% of the results in each of the tails. And if you're using four standard deviations of the mean, he simply says that's approximately 0% in the tails. All we need really is the mean and the standard deviation to start saying remarkable things about the normal distribution. He provides a quick example with USD versus United States dollars versus the euro. Apparently at some stage it was similar to a normal distribution. The mean was $1.2 and the standard deviation was $0.05. So what's the probability of the rate being greater than or equal to $1.3 per euro? Well, it just works out into this situation where he's working out the probability of it being in the rightmost tail. So it works out as the probability in the right-hand tail is 2.5%, because two standard deviation of the mean were 0.1. He did 1.2 plus 0.1, which equals 1.3. So we are actually dealing with 95%, two standard deviations of the mean. It was just the sort of that result we always like to find and remember. So 2.5% in the right-hand tail. There was also, of course, 2.5% in the left-hand tail, and the middle bit was the 95%. Okay, so moving on to chapter 18, one of the last chapters, he is talking about understanding presidential election sample sizes and opinion polls. He starts off by saying 95% within two standard deviations of the mean. More precisely, it's 95.44, but everyone likes to use 95%. He talks about sampling, and the idea is that from a small random sample, you can get information about the whole population, because sampling outcomes from the random polls follow the normal distribution. He then goes through a number of formulas, which I'm not going to explain because I don't think it'll make that much sense on the audio. But he reaches a final sort of favourite formula, and he says one of his favourites is margin of error for a poll with 95. For example, a poll reports 65% for the candidate. The sample size was 1,000 people. The sampling error was plus or minus 5%, and this is apparently how these things are often reported in America. So then he wants to do some analysis based on what he knows about normal distributions and sampling. And he says a key to this is to know that unless otherwise stated, the result is true with 95% probability rating. So he starts doing some calculations. 95% of results are between 60 and 70%, and the two tails are 2.5%. So there's a 2.5% below 60 tail, and there's a 2.5% above 70 tail. Now he says we can check the margin of error for a poll with 95% probability correct. So he does 1 divided by the square root of 1,000. He gets 0.0316. So sampling error should be 3.16%, he says, not the 5% stated in the report. But this sort of thing, where they don't necessarily state it, precisely in the report. He says it's all too common. Let's move on now to chapter 19, and it's his conclusion for the whole book. Aczel says that probability theory is a window on the random. It is a skill to estimate randomness, but one which does not understand randomness. He says it's about humanity and the laws of the universe. There's a bit of a spoiler coming up, so I want to talk about the puzzle questions which Aczel poses at the end of the book. I did quite well on these puzzle questions after making notes and being careful. Question 2 are mostly about, questions 1 to 10, are mostly about probability tree diagrams, taking care with, if it says without replacement, and that sort of thing. Questions 11 to 16 all use that situation where you can do 1 minus the complement. And some of them are really far out. You can really work out some incredible things using this 1 minus the complement idea, which he explained in an earlier chapter. And, well, let's face it, a calculator, because taking something to the power of 50 can just be done so easily these days on a calculator, but it wasn't so easy in the past. It also needed to take care of dying and surviving in these type of questions, so that you're using your complement correctly. If the statement, in some situations, it could have asked you the probability of dying or the probability of surviving, and obviously that makes a difference in how you finally express your answer. There were then quite a lot of novelty questions. There was a birthday problem. There was a slap 'em through type of expected gains problem. There was a Bayesian type of problem which I solved with the probability tree, and some other examples. So that's the end of my book summary for another really fantastic book by the great author Amir Aczel.